Ladies and gentlemen, we are back for another episode. We've seen neural network structuring, we've understood the idea of gradient descent. Today, let's put a lid on all of this and understand how gradient descent actually happens. And how that happens is by the backpropagation algorithm. Of course, by now, we know the structure and the general operation of a neural network, that is, activations in one neuron in one layer influence activations of another neuron in some other layer, and so on and so forth, till you get what you want, which is activation in your output answer layer. And we also know that activation at each individual neuron is the sigmoid function of the weighted activations that are coming into it. This much we know from our previous episodes. Now, to understand backpropagation, let's strip it all down. Forget the sigmoid function that we push it through, forget the biases that we have to consider, forget the hundreds and thousands of neurons and their connections, forget all of that. Let's just consider interaction between two neurons, only two neurons. What is happening here? Literally, these two neurons, one from the input layer connecting from the input layer to the output layer. They're connected, and their relationship, for simplicity's sake, because we forgot biases and everything, let's just say y equals a into w, where y is the output neuron's value, a is the input neuron's value, and w is the weight of their connection. Before we start training, we know to get the correct answer, the output neuron's value should be 1, for example. So that's maximum activation of that output neuron, correct answer. Let's say we want it to be ideally 1. And also for our example here, we know what the input neuron is feeding in. So let's say, for example, that's 2.5 as an input value coming into our neuron. But what we need here is the weight value. What should be the weight value? How much should we tweak this weight to get to our correct answer, that is 1, right? We don't know what the weight should be. So let's randomly initialize it and say a weight, we've randomly initialized it to 0.5. Which means if we plug this weight 0.5 and the input 2.5 into our y equals a into w, we will get an output as 1.25. But that's not what we want, right? We want the output as 1. Which means if we had weight as 0.4, let's say, then if we plug that into the equation, we would have got our output as 1. But hey, hindsight is 2020. We didn't know, so we initialized it as 0.5. And now we've got to train it and adjust it. So required output is 1 and the output we have now is 1.25. Actually, let's say I initialized it a bit too ideally, like initializing it 0.5 and wanting it to train down to 0.4 is a bit easy, so we'll see how that goes in the future, but for now this is the case. So required output is 1, the output that we have now is 1.25. we got to train and bring it down, right? So what we got to bring it down is, as discussed in the previous video, we have to get the cost function of this error and bring that down. So C, the cost function, is the current output minus the required output squared. If we plot the activation versus the weight, just to check, we get a graph that looks like this. Right now we're at output 1.25, so we're at weight 0.5. And if we need to slide down to the output 1 that we want, we need to get weight 0.4, right? And just to solidify this even further, if we plot the cost function as well, we get a parabola that looks like this. And you see the minimum of the pit of this equation is at 0.4 weight. So that's where we got to descend down to and settle to get our correct answer, right? Now to begin gradient descent, we take the slope of the cost function as we discussed in the gradient descent video, which gives us 2 into y minus y dash. Now the thing is, we don't have control over the output, do we? So we don't need to differentiate with y. We have control over the weight, so we need to differentiate dc by dw. So when we do that, we've got to break it down with the chain rule, of course, which makes it 2 parameters. That is, the first one, how much the weight affects our output and how much our output affects our cost error. So dy by dw, how much weight affects our output, is just the input, which is 2.5. And the other component, dc by dy, is how much the output affects our cost, which we've already done, 2 into y minus y dash. So if we put it all together, we get the equation with respect to the weight dc by dw, and that's 5w minus 2.5, which is the input. Finally, there's also one more thing to consider, the learning rate, the resolution step of training that we've spoken about in the previous video. So we have to consider that in, call it small r and say it's 0.1, the value, and factor it into the training equation. And the training equation starts to look like this, right? The training equation is the new weight is equal to the old weight minus a multiplication of the learning rate into the dc by dw differential. Remember, the goal is to adjust the weight and update it and keep adjusting it again and again. Now at this point, I realize that the input weight that I considered at the start, 0.5, is a little bit too nice and a little bit too ideal. As I said earlier, considering it 0.5 and the answer has to be 0.4, we'll iterate to 0.4 in no time at all, very quickly. So my bad. For this maths, let's just consider the randomly initialized weight as 3 instead of 0.5. So the randomly initialized weight that we start with is 3, not 0.5. And we need to get down to 0.4. So if we consider the randomly initialized weight to be 3 and we plug that into our training equation as W previous, the previous weight, we get a new weight as per calculation as 1.75. So we've adjusted the weight and we tweaked it and it descended down from 3 to 1.75. That's one iteration. So we take this 1.75 that you got, plug it in again as previous weight, and we get another new weight updated as 1.125. You see it's descending again. We keep updating these weights and descending down till it converges to 0.4, which gives us the correct weight. And we know that it's the correct weight because it is the local minimum. And also if we just take this 0.4 and plug it into our original equation, y equals a into w, it'll say about 2.5 into 0.4 is in fact 1, which is what we want as our correct answer. And that, ladies and gentlemen, is gradient descent and the backpropagation algorithm, essentially getting ourselves a training equation first and training that model to update the weights according to the equation in order to gradient descend down and converge to our minimum value, reducing the cost error and arriving at the output that we require. In our case, in this example, of course, the output is 1, that is full activation of the output neuron. If this output neuron was part of an output layer of a number recognition neural network, it would fully activate that correct answer number. So if you showed it the number 9 as input, the last neuron in the output layer, which is the number 9 corresponding to number 9, would show full activation output 1. If this were perhaps an image recognition network of dogs and cats, it would fully activate the dog neuron at the output and say, I think it's a dog, not a cat. You get the idea. Thank you so much for watching. Next video, of course, we can finally put all of this theoretical understanding into practice and dive into some code. It's been too long. Like, share, subscribe. Comments as always, most welcome. Thank you so much for watching. And yep, I'll see you next time. Jan Barpe.